Greetings everyone, this is Team 35 and these are the team members. I am Priyank.
I am Andre Martin.
I'm Rohan Chakra.
And I'm Adil.
So the problem statement was to detect and track objects in a video using the given mesh models. And our approach to the problem was to convert the mesh models to corresponding edge templates and then use OpenCV algorithms to do the tracking. Our software can now successfully detect and track objects in a video stream.
The first thing we did was we compared all the available feature point detectors based on scale, rotation, blur, and lighting. We planned to use a shift-based feature detector with a scale and rotation variant along with the flank-based matcher. However, the accuracy was compromised, and even though the speed is increased, this was a trade-off we had to accept. We also tried using a brute force matcher, which increases the accuracy. However, when we tested it out, the frames per second. After trying out various combinations of feature detectors and matchers, we finally settled on using a multi-scale edge-based template matcher.
So there were three major objectives for the first release. First, converting the mesh models to line templates. Second, extracting the edges from the 2D video. And finally, to detect the object in the video and then logging its position.
Now coming to research, there are two major ways we can approach this problem. Either a textured model-based approach or a textureless model-based approach. It all depends on the type of object you're looking at. So initially we set out to try a textured model-based object tracking approach. The major concepts involved in this task were to extract feature key points from a video frame. So the main idea of what a feature key point is to analyze a frame and then realize what are the major regions of interest in this particular frame. Now once you have selected those regions of interest, you extract information from each of those key points using feature descriptor algorithms.
In order to match the model to the corresponding object in the video, we need feature descriptors. A feature descriptor is an algorithm which takes an image as an input and outputs feature descriptor vectors. Now these descriptors can be used as a numerical fingerprint which can be used to distinguish one feature from another.
The rotation test shows how the feature descriptors depend on the model's orientation. As shown in the graph, all descriptor algorithms are rotation variant except the brief algorithm.
So next we look into the scaling test, which tells us about the feature descriptors dependency on the feature key points. The surf and the sift algorithms show a good stability as compared to the other algorithms because of the expensive key point size calculations. The blur test tells us about the robustness of the feature descriptors against the blur. As seen in the graphs, all the feature descriptor algorithms show good results in this test.
Now the lighting test shows how robust the feature descriptor algorithms are against lighting changes of the image. All feature descriptor algorithms work very well in this case. The major reason that all these feature descriptor algorithms work really well is that normalization makes them robust against all lighting changes.
So the next important concept in our approach was that of the matchers. We had two matchers available to us, the brute force matcher and the flan matcher. Now what the brute force matcher did was it extracted the descriptor out of a feature point and matched it with every feature point of the image2 dataset, and the closest match was returned. The next one, which is the flan-based matcher, was a collection of highly optimized algorithms used for fast nearest neighbor calculations and searches to get the closest matching descriptor.
So I'll be talking about the strategy we used to tackle the problem at hand. The problem with untextured models is that we cannot use feature descriptor or feature extractor algorithms or OpenCV, which uses color or other texture-based parameters to detect and track the object in the video. So we had to use a different approach.
So the first step in our approach was to get all the projections from the mesh models that were given to us. We did this by rotating the mesh models in all the possible orientations and the ones which were the most common to be encountered. This was a crucial step in our process because it would yield us with all the edge templates that would be later on used for the multi-scale template matching algorithms.
The next important step was to convert the video into such format so that we could match it with the edge templates of the models we retrieved. What we used was the canny edge detector algorithm of OpenCV, which extracted the edges from the video frame and allowed us to just focus on the edges and managed to get rid of all the color and text details of the video. This allowed us to just match the edge templates of the video with the edge templates of the object, thus helping us to increase our efficiency multifold.
Out of the numerous edge detector algorithms available, Canny and Sobel are the two most popular ones, with Canny being more accurate and efficient.
Finally, the most important step was to detect and track the models in the video. We had to match the edge templates of the frame with the edge templates of the models we generated. To do this, we had the match template function of OpenCV to help us. So we retrieved the brightest pixel and the dimmest pixel from the match matrix and extracted the respective locations of them. Now from these set of bright pixels, we selected the brightest pixel out of them and drew a bounding box on the region of interest. We appended the location coordinate of the object into the respective log file of that particular model.
Now I shall be presenting you with a demonstration of the code. First, I shall show you the directory structure. The directory structure, the main directory, has the data directory, which has the data pertaining to every model, the output, which stores the output pertaining to every instance of the model, and the source directory, which has the code related to the main program of the file. In the data directory, we have each directory maintained for a particular mesh model. In every directory, we have a mesh, template, and training video folder. The training video contains the video of the mesh model taken from a projection point of view, and the templates contain those particular projections extracted from the training video. Heading over to the source directory, which is the home of our main module. The main module of the program is run so as to obtain and log the positions of the particular objects in the image screens or the video screens and log them into the respective logging folders, which are stored in the output folder. Let us run the main module for a file called peta2 and see the output. As you can see, the blue syringe is being tracked in every frame and is being put into a bounding box. On the top left corner, you can see the video that shows all the edges that are extracted from the video stream. These stills are taken and matched against the templates that are obtained from the mesh model and are logged into the logging file. Let us show you the output of the logging file. We enter the output directory, the syringe body, and the instance 1. Displaying the log.json file for that object, we obtain the x coordinate, the y coordinate, and the timestamp of the object in the frame of the video.
Currently, the software focuses on detecting only one object at a time. By the next release, we plan to increase the scope of our project so that multiple objects can be tracked and detected.
Since identifying and tracking multiple objects will lead to more computation, we also plan on increasing the efficiency and the accuracy of our algorithm so that multiple objects can be efficiently tracked and detected.